Hi, welcome back to Math 521. These are a little bit of discussion for the Notes 19. I had asked people to pick one of the three topics I had suggested for the last topic of the term, and there was not any strong agreement on which topic to pick. So I thought I might give sort of short presentations on all three of them, so that everyone can see what they're interested in. I don't have to lecture for an hour and a half on each of them, so yeah, seems fair. I have notes prepared on them, and I'll just give a little bit of commentary on each of them um, in turn. First one, the one up today, is incompressible flow and how it's approximated with the finite element method. If you look at the notes, there's two parts to the written notes that are posted for this for the notes 19. The first part is sort of a general introduction to the Navier-Stokes equations, and that's the whole story. Time-dependent Navier-Stokes equations, and really, I'm going to talk about the interesting thing with the discretization of the incompressibility condition. But the real effort in making a good solver for fluid flow is handling high Reynolds number, so large convection terms. And we haven't talked about convection problems or hyperbolic problems at all in the class, and we're gonna stay that way. So just so you know, if you get into that game, there's a whole side of the story that we haven't covered in this class. When you get into the correct way to approximate high Reynolds number flow, it's really talking about how to handle things that are approximately discontinuous in the limit as the okay, I just said it now. I'm trying to remember the name of the parameter. The Reynolds number goes to infinity. You have shock dynamics, and then you can have discontinuities, and to handle those correctly on a grid, whether finite difference, finite volume, or finite element, requires some specialized techniques, which again we're just not going to cover in this class. So after the general introduction, then it goes to some functional analysis of what the steady Stokes problem looks like. So this is an elliptic problem like the Poisson problem, but with the wrinkle of the incompressibility condition. And then after that, then there's the discussion of the discretizations. You'll see in the notes there is a finite difference discretization based on a marker and cell grid. And if you, that gives you a really, like many of the things that we've done with finite differences, it gives you a really concrete starting place for what discretizations of these problems look like, and the structure of the linear algebra problem that comes out. And the same kind of structure comes from a finite element discretization. And in the analysis and in the finite difference discretization, there is subtlety, not that subtle if you get it wrong, about the compatibility of the spaces you pick for the velocities and the pressure. This is called the Imp-Sup condition, or the Bretzi-Babushka condition, BB for short. and you'll see that condition in the discussion that comes up. And again, you can follow through the main notes to get all of the details that I leave out in the overview discussion I'll give next. Okay, let's start our discussion of the steady Stokes flow. Just look at it in 2D, in a bounded domain with homogeneous Dirichlet boundary conditions for the two components of the velocity. And you have a momentum balance. This is a viscous term, pressure gradient, and then some external forcing. And when we talk about incompressible flow, it is that the divergence of the velocity is 0. Okay, this is a combined problem for a vector u, two components in 2D, and this pressure P. And you'll notice if you've never seen this before, this is a kind of an interesting problem because if you think of this as the equation for u, then there's no equation for P, right? There's just an extra equation for u. And one of the ways you can think of this at a high level is you're solving for u, which has a constraint, this incompressibility constraint, and the P is the Lagrange multiplier for that constraint. Now let's start to get a handle on what this problem is like. First of all, you have to realize that P is only determined up to a constant because it only appears as the gradient of P, so you can change P by any constant that you want. There's an arbitrary constant in the pressure, and typically, on the analysis side, you fix the constant in the pressure by requiring the integral of P to be 0. This makes the average value of P 0. And if you look for P in our usual L2 space, but you want to restrict the space to only functions whose integral is 0, that gives you a subspace of L2, typically denoted this way, where you have L2, but you mod out the constants. That's what this is saying. Okay, so now you know P is only determined up to a constant. So let's do formal work to see what this looks like. So let's say P, I'm going to think of as something I'm going to determine later, okay? And I'm going to figure out what U is in terms of F and P. Well, it's just formally, I solved the Laplace problem with a right-hand side that's grad P minus F, right? And it's important to remember that when I talk about this inverse Laplacian here, it is the inverse operator with these Dirichlet boundary conditions, okay? So if you told me a P, I could take its gradient, I can figure out this right-hand side, and then I can figure out the velocity U. What determines the pressure, though, is that you have to pick it so that the divergence of U is 0. So if I take the divergence of this thing, I get an equation for P. Now the interesting thing is there's a Fredholm alternative going on. Think of this like a matrix which has a null vector. It's symmetric. And the only way you can have a solution is if the right-hand side is perpendicular to that null vector. But it is because if you take the gradient of anything, right, then you have no constant term, right? You take out that constant term. So this is a solvable problem. Well, okay, it actually requires some thought. let me at least tell you why you expect this to be solvable in sort of reasonable domains. Think of a domain without any boundaries in it, okay? So this would be a periodic cell or all of R2, so all of two-dimensional space. There's no boundaries. And in that case, these operators commute. And so you've got Laplacian inverse of Laplacian of P, which is the identity. Well, okay, now you have to be careful because the Laplacian of a constant is 0. So it's the identity on this space that we're thinking of for P. So if there's no boundaries, P is just the gradient of Laplacian inverse of the right-hand side. So that's pretty straightforward. So let's get into some functional analysis, waving our hands at some spots. I'm going to make a specialized weak form of this problem. I'm going to look for U in a space that's H01. Okay, that's a sort of typical thing that we have. But I'm going to modify it. So I'm going to look at that space, but I'm going to restrict it to divergence-free functions. Okay, so that means I don't have to worry about this condition anymore. I've just made my space so that condition is true. Okay, so here I've got this thing. I'm going to test. I'm looking for a solution U in J. I'm going to test with test functions that are in J. And of course, if you do that, then you can integrate by parts. Oh, there should be a minus sign here, right? And this term falls out whenever you test with something in J. So you just get basically a two-component Poisson problem, Poisson-looking problem anyway, for U in this space J, which includes the constraint. And you can take energy estimates and show that the H1 norm of a solution of a weak solution of this problem is bounded by the data. And of course, this gives you uniqueness, right? Because if you have the difference, it's all linear. You have the difference of two solutions, then the corresponding f for the difference of the solutions is 0, which means that the difference has to be 0. So we have uniqueness. Now, if this was a finite dimensional linear algebra problem, you know that if you have unique solutions, then you have existence of solutions. And in the infinite dimensional case, you still have to do a little bit of work. But if you know what the Riesz representation theorem is, this gives you a guarantee of a weak solution to this problem. Now, it sounds like the story is over, but actually so far we just have a candidate solution of the whole problem. Okay, now why is it only a candidate? Well, this is what I'm supposed to solve, and I can put the U that I found and test with test functions in J and get it to work out. But I want to be able to test with all functions in H1 to actually see that this actually is a solution. This is equivalent to saying, is there actually a gradient of P that can handle the stuff that's in the space that I didn't test against, right? So I'm going to test with all functions in H1 with 0 boundary conditions. It's already satisfied for the restricted subset of H01 we started with, but now we want to see what happens. So remember, I've found that I've got a bound for this u in terms of f. So I'm going to have, I'm going to multiply by phi. I'll integrate by parts. I'll get this thing. I'll have two terms. I'm going to have f with phi, and I'm going to have, I'll integrate by parts once with these guys. I'll have the gradient of u and the gradient of phi, but the gradient of u is bounded by f that we found before. And so with the u that I know is a candidate solution of the whole problem, I have this estimate. Okay, and this is true for every test function. Okay, and now we get to something which is going to be true for all domains that you could reasonably pick in science and engineering, but requires some special techniques to figure out the class of perhaps bizarre domains where this doesn't hold true. But in all reasonable domains, you'll have something called an imp soup condition. Okay, and that says there is an alpha bigger than 0. So any p that you pick, okay, right, you can find a phi in H1 so that this thing is big in terms of the norms of these two things. This is somehow saying that there are there's a non-zero angle between some subspaces going on. That's essentially what this is saying. So all domains, all sort of reasonable domains will satisfy this. And if that's true, then if you look at this thing and you pick the phi that goes with the p, and you put it all together with the inequalities chaining, you'll see that the p has to be bounded by the data. Again, that gives you uniqueness, and with some functional analysis, you get existence of the p that then satisfies the whole problem that you're interested in. Okay, there's a little bit of functional analysis. That's not really, the usual kind of thing in a numerical analysis class, but this idea is mirrored in the finite element approximation, so I thought I'd show it to you in this continuous case first. Okay, so here is the weak formulation that we want to get to for the Stokes equations. Now it's pretty straightforward, right? You're going to pick a subspace of H01 for U and a subspace of L2 mod R for P. And then you're going to test the momentum equation with okay, oh, I'm mixing up my my continuous to discrete. Okay, let me start again. If we had the space J, then we could build a finite element method out of that. But a basis for J is not local. So typically, you don't do that reduction. You just test the momentum equation with all test functions in H01 and the divergence-free condition with test functions in this L2 mod R. Now, what this means when you're restricting to functions that have zero boundary conditions, this means that the divergence of U is 0, which means you really are sitting with U in the space J, and then you're testing this with things in both J and not J in H01. So this is the same as it was before. You'll get the same solution as you had before, but this is more amenable to a finite element discretization. Okay, so now let me pick up again. So you're going to pick subspaces for the velocity and for the pressure. And then you're going to, it's a Galerkin finite element method, so you're going to have the same space of test functions as for solutions. And so you end up with these matrices. Now you notice that there is a similarity between these two terms if you think of these subspaces. And so what happens is that the matrices that come out here are transposes of one another. Now you can put a minus sign here, and then this is a symmetric matrix. It's called a saddle point matrix, right, with some blocks, right? It's defined in terms of these blocks. It is symmetric with the minus sign here. Unfortunately, it is not positive definite, so you can't use conjugate gradient method on it directly. You have to use less appealing Krylov subspaces methods that don't require the positive definitenesses of the matrices. And they work much less efficiently than conjugate gradient. Now, you cannot pick these subspaces arbitrarily, okay? You also have to have a discrete version of the inf soup condition, okay? And so it's phrased exactly like this. Now, the study of finite element combinations that satisfy the inf soup condition has received a lot of attention in the literature over the last 40 years, 4 decades. Well, it is something you have to get right, and maybe it is such an interesting problem to consider because the obvious thing that you might do does not satisfy this condition. We're used to starting off with finite element methods thinking of triangles. And sort of a natural thing would be to take the usual conforming piecewise linear elements on triangles for U, and for P, just take piecewise constant values on triangles. But if you look in the notes, you'll see that that is a spectacular failure, and hidden there is that that element pair does not satisfy this condition. Now, if you go on in the notes, you can see a little bit of a fashion show of elements that do work. And if you are using a package that can handle incompressible fluid flow, you'll see one of those, most probably, you'll see one of those in the list of things that you can use for those kind of problems. Just to go back to this system, this kind of saddle point system also comes up in some kinds of optimization problems, and so it is well studied. And I don't want to tell you that this is the only way that you can solve this problem, but I just wanted to show you one way, which is to do the Schur complement. Okay, and that's essentially the discrete version of what we did here. You can apply K inverse formally to this and take the gradient of the resulting u and set it to 0, and this is the equation that you get. Remember, in the continuous case, this is the operator which, without boundary conditions, is just the identity. And you can certainly look at this and go, it is a symmetric, positive, definite operator. Okay, could be negative definite, so don't quote me. But either way, this is something you could use conjugate gradient on. Of course, at every step of the conjugate gradient iteration, you have to do a solve with the stiffness matrix. So that's going to be the time-consuming part. But you know that there are multi-grid methods, and could be conjugate gradient, preconditioned conjugate gradient methods inside of an outer conjugate gradient method on this problem. And under this BB condition, you can show that this matrix has a condition number that's independent of H, so it will converge quickly. Remember, in a sort of an idealized setting, this is the identity matrix, and so you're expecting a good behavior from this. So this is, in some literatures, this is called the pressure equation. This is just one way to handle this saddle point system that comes up. If you want to know more about saddle points systems and various ways to solve them, my colleague Chen Greif in computer science is one of the world experts in those kind of problems. And so you got a local person to talk to if you want. Okay, again, this is just a first glimpse into incompressible flow. And it's all about handling the incompressibility condition in the elliptic problem. And the other main difficulty is appropriate handling of the convection terms in high Reynolds number flow. And that's a story which I will leave you to follow on your own through other courses if you like. Okay, so this is the first of 3 sort of short lectures, and I will follow up with the other 2 sometime later next week. Hope all is well.